Okay, so we left off last time with me being a little bit overly dramatic and saying that maybe R was broken. Questions before I pick up there? Okay, so I'm going to continue on that theme a little bit just to play this out for fun, and we'll see if Python is also broken. So if I do 0.3 minus 0.2 equals 0.1, also says false in Python. So if we're claiming R is broken, then Python is also equivalently broken. Okay, so let's switch back to R and start to get a sense for what's happening and in what context this particular issue seems to arise. So I'm going to first switch one of the options in R so that I actually print out more digits, and that's going to help us see what's going on under the hood. Okay, so now if I enter A and B, and if I write out A and I write out B to the screen, you can see that these are not being represented precisely as 0.3 or as 0.2. They're being represented as numbers that look very, very, very close to those numbers, but are not quite exactly equal to those numbers somehow, someplace way out here in the number of decimal places. So if we actually count these digits, there's 4, 8, 12, 16 here. And if we do the same thing here, what we'll see is that there are essentially 16 digits of accuracy in representing the numbers. So this digit is not accurate, but if I then take this digit and use it to round this one, we'll see that it's accurate up to, essentially up to this place, which is the 16th place in the number. And similar fashion here. Okay, we can continue on this vein. We could look at, for example, 0.1 and see that, okay, 0.1 is not represented exactly as 0.1, and indeed, if we start thinking about subtracting these two, they're not necessarily going to come out to be exactly the same as what we get in the representation of 0.1. So they're going to be very, very close, but they're not going to be exactly the same. And if I do A minus B, we'll see, okay, pretty darn close, you know, something like 1 times 10 to the minus 16th difference between if we subtract 0.3 minus 0.2 and if we're comparing it to how 0.1 is represented, but they're not exactly the same, and that's why when we do equals equals, we see that it's actually false. Okay, so what's going on here? Well, one way to start thinking about this is to start thinking about the fact that we can't represent 1/3 exactly in base 10. All we can do is represent it as 0.3333 and just keep going on into infinity, and we'll get an increasingly precise representation of 1/3, but we'll never get something that's exactly equal to 1/3 if we try and represent that in base 10. Okay, so questions at this point? Okay, so there's this notion that's going to help us in thinking about these questions called machine epsilon, and machine epsilon is basically the it's used to define the accuracy of how we can represent real numbers, and it's basically the smallest number that when I add it to 1, it gives a number that's different than 1 on the computer. So if I take 1 plus x, I'm going to see whether or not that is equal to 1. And the value of x that is the smallest x, such that this is not equal to 1, is going to be machine epsilon. So it basically represents some measure of sort of the accuracy with which we can represent numbers. So we've already seen here that we're accurate about to 16 decimal places there. So I could start playing games like the following. Well, first I can say, okay, can I represent 1 times 10 to the minus 16? Well, okay, I can represent it, but it's only represented with accuracy. It's not represented precisely in the same way that we've seen with these other numbers. It's represented with essentially 16 digits of accuracy, which gives us accuracy down to 1 times 10 to the minus 32nd, because the magnitude of the number is 1 times 10 to the minus 16. So I can play games like this. I can say, what if I try and add 1 times 10 to the minus 16 to 1? What do I get? I get back 1. Okay, so I've tried to add a number to 1. I've gotten something that's not any different than 1. Okay, so I'm not accurate in doing that calculation. if I take 1 times 10 to the minus 15 and add 1 to it, or if I take 1 and add 1 times 10 to the minus 15 to it, I can see that I do actually, if I count these, this is actually in the 15th place, and I am actually able to get an accurate representation up to this place of doing this calculation. And if I do 2 times 10 to the minus 16 and add it to 1, I can get an accurate, reasonably accurate representation up to a certain number of places of adding 2 times 10 to the minus 16 to 1. So essentially somewhere between here and here is where everything goes haywire, and adding something to 1 just gives me back 1 itself. So I mentioned the dot machine, the sort of special object dot machine, this sort of hidden object in R that represents a lot of these concepts. And if we look at double dot eps, that is R's name for this concept of machine epsilon. And if we ask what that is, it says indeed that's 2.22 times 10 to the minus 16. So essentially right essentially what we were getting by sort of doing it by sort of a grid search to try and figure out what that number would be. And let's see what happens if I try and add 1 to machine epsilon. Okay, so that seems like it worked. So it seems like this is more or less on target, that I have an idea of what this value is. Okay, so let's start thinking about why 10 to the minus 16, why 2.2 times 10 to the minus 16, and what's happening under the hood when we're actually working with these kinds of numbers. Okay, so we sort of have to go back to basics of how we represent numbers and think about scientific notation. So if we go back to, I don't know, what was this, like chemistry class? We're used to thinking about like Avogadro's number, 6.023 times, what is it, 10 to the 23rd? Okay, and the nice thing about representing a number in scientific notation like this is we're able to use these digits here to sort of represent the accuracy of the number. And then we're able to use these numbers here to basically scale numbers up and down and be able to represent very large numbers or very small numbers. Okay? So what we get here gives us sort of the precision of our answer, and then this allows us to vary the magnitude of the numbers that we're representing. So basically on a computer we're going to do this, but we're going to do it in base 2 for reasons that have to do with the fact that we've talked about using bits and zeros and ones as how a computer stores information, and it's actually faster to do calculations on a computer, to do the arithmetic if we have things stored in base 2 instead of trying to take bits and make those into base 10 numbers and store base numbers in a 0-1 representation. So the idea is that we're going to represent numbers like this, but we're going to do it in base 2. So okay, so I guess one thing that came up when people were developing this was they said, okay, well let's represent numbers in a form like this, and then we need to make a choice about what base we're going to use, and that led to discussion of, well, can we do computations more quickly with base 2 than we can with base 10. So the other thing I just want to point out, and this goes back to what I was saying here about precision, is that the nice thing about representing numbers like this, which basically we can call this a floating point representation, because this, by having the base, we're basically allowing the decimal point to sort of float back and forth and represent either very large or very small numbers. There's sort of an example we can take here of. Suppose that we are thinking about doing this multiplication. So if we do this multiplication, obviously the answer is 0.0144. And I can represent that in floating point notation as 1.20 times 10 to the minus 1, and I can get the result back and represent that as 1.44 times 10 to the minus 2. And you'll notice here that in both of these cases I have 2 places of accuracy with which I'm representing, or two values with which I'm representing numbers after the decimal place. But what's happened here is the decimal point has basically floated here from being order of 10 to the minus 1 to being order of 10 to the minus 2. On the other hand, if we didn't have this ability of moving the decimal place back and forth, And I thought about writing out the number like this and then multiplying it together. And if I could only store 3 digits here, for example, well, then I'm going to lose the second 4 here when I do this multiplication and then try and store the result with only 3 numbers to store the result. And the reason is because this 0 is basically taking up space in representing my number, and it doesn't need to take up space because I could more concisely represent it using the exponent here. So basically, if I did this in sort of fixed, what do they call this here? If I fix the decimal point, then I don't have this ability to sort of transfer these leading zeros up into the exponent. Okay, so questions about that? Okay, so here's how computers these days generally represent real numbers. So I've written it there. I also have it up here just so we can, as we go through some of the demonstrations, it'll be nice to just have this up here for us to remember. So it's basically, we're going to represent positive or negative numbers by taking -1 and either raising it to the 0 or raising it to the 1. So we're going to use 1 bit to represent whether a number is positive or negative. And then we're going to have to represent a number, as we've already seen, we're going to have to represent it as a number times the base, in this case 2, raised to an exponent. So if we think about how we're going to store numbers, well, we're only going to be able to allocate a certain number of bits to store each number. Otherwise, if we allocated more and more bits, then every number would take up a huge amount of space and we'd be able to store fewer numbers on the computer. We'd use memory and disk less efficiently. So we're constrained by having some fixed amount of space with which to store a number. So in general, this is going to be 8 bytes or 64 bits. And so we can basically think of how we're going to allocate those 64 bits to either the D part of the number or the E part of the number. And let's see. So there's a 1 here in the starting position, and that basically makes sure that we have a unique representation of every number. You can see the example here. We could either represent it 1 as 1 times 2 to the 0, or say 0.1 times 2 to 1, or 0.01 times 2 to 2. And by putting the 1 out there, we prevent that from happening. We prevent that, give us that uniqueness. Okay, so this is sort of, the 1 is there and it's sort of hidden. We don't usually think about it. We just know it's there by default, the 1 here. Okay, and then in general, the choice was made as people were developing computers at different stages of how to represent numbers on the different stages of development of computers, to represent the E with 11 bits, okay, and then to use 52 bits to represent the D part. Okay, so the question is, what's the trade-off between that allocation of doing 52 bits here and 11 bits there versus more than 52 here and fewer than 11 there, or fewer than 52 here and more than 11 there? What's the benefit if I have more than 52 bits for D? Yeah.
You have higher precision, or like within a scaled number that you have a greater set of numbers that can be represented.
Right, so I have more digits. Let's ignore the 2 to E and just assume that I'm multiplying by 1. So I have 1 point D times 1. If I have more digits, instead of 52, if I have 53, 54, 60 digits, I'm able to get a more accurate base 2 representation, or equivalently a more accurate base 10 representation, basically more than the 16 digits that we've seen, if I allocated more to the 52 to the 1 point D part of this. But if I allocate more to the D part, that means I have to allocate fewer to the E part. So then what happens? Okay, so I can't get as big a number or as large a negative number as I could if I keep E with 11 bits, or if I use more than 11 bits. Okay. So basically, if I take 2048, which is basically the maximum I'm going to be able to get, then 2048 minus 1020. what is it, 1023. It actually ends up being 2047 is the maximum. So I would get 1024, and I can think about what's the size of 2 times 10 to the 24 in base 10, and that gives us an idea of what's the biggest number that we could represent. So if I'd use more than 11 bits, then this would be a bigger number, and I could represent larger numbers on the computer. So that's the trade-off. This trade-off was made very carefully when people were thinking about this to try and balance this precision versus magnitude of numbers that we want to represent. Okay, so now we can also, now that we've seen this, we can answer a number of questions that have already come up in terms of things that I've posed to you as being sort of weird things that are going on. So we've already seen, okay, 0.1 cannot be represented exactly. Well, what about 0.5? Looks like that can be represented exactly. So why is that? Well, 0.5 is just 1/2. That's 2 times 10, 1 times 2 to the minus 1. It's a base 2, it can be represented exactly in base 2. Similarly with 0.25, but not with 0.26. Similarly with 1/32nd, but not with 1/33rd. Okay. So those are that tells us, which numbers do we expect to be able to represent exactly on the machine. Okay, so now let's think about this idea of how big a number can we represent, and we're going to see that in R we would be able to see this if we did it in Python as well, or in C or other languages. That indeed what we've just talked about does determine how big a number we can use on the machine. So first I'm going to try and do this a little bit naively. I'm going to take 2 to the 1024. So this is the 2040. This is the E 2047 minus 1023. And I'm going to say, how big is that number? Okay, so I want to do that and say, okay, in terms of base 10, how big is that number? So I'm going to take the log of base 10. Okay, so it says it's infinite. So I'm already sort of starting to run into the limits of the fact that I can't represent big numbers, because I was trying to figure out what's the biggest number I could represent, and it turns out that I went a little bit too big and I can't represent that number, so I can't get the answer to my question. So let's make it a little bit smaller and see if I can represent 2 to the 1023 and see what that is in base 10. So that's 1 times 10 to the 307. So somewhere between here and here is the largest number that we can represent. And in fact, it looks like it's about 308. So we're thinking it's probably around 1 times 10 to the 308. That's about the biggest number that we can represent. And if I actually, I'll switch back to the PDF. So if we go back to, I don't know, I guess this was high school math, or I'm not exactly sure when this was, but we can play around with bases. And we can say, what is this value? We can do it in terms of math, instead of trying to do it on the computer, where we start to run into the limitations of how we represent numbers. Well, that's this representation, 1024 divided by 3.32, and that's right around 308. So we could do a similar calculation in terms of the smallest number we could represent, which would be 1 instead of 1 minus 1023 for this E minus 1023. Instead of 2047, it would be 1, and that would be minus 1022. And that's going to show us that the smallest number we can represent is around 1 times 10 to the minus 308 as analogously. Okay, so let's actually look and see what's double.x max. So in R's terminology, that's the largest number we can represent, right around 1 times 10 to the 308. And what's the smallest number? Right around 1 times 10 to the minus 308, in this case 2 times minus 308. And if we try and add together or multiply together numbers and get something bigger than that, R is going to give us back, presumably in this case, inf. Potentially might give us an NA in certain contexts. Okay, questions? Alex? Yeah.
Why are X max and X min not the same?
Yeah, so it has to do with this notion of we can represent, with 11 bits, we can represent 2048 unique numbers. So we can think about what that means. And if we represented that as 1 up through 2048, then we could presumably do 2048 minus 1023, that would actually give us 1025. And 1 minus 1023 would give us 10 minus 1022. So this isn't symmetric around 0. So then we might say, okay, well, let's actually make it 2047 and 0. And so now we've got 1024, and now we've got minus 1023. But because of the fact that we have the 0 in the middle, we sort of have an odd number of values that we need to represent. And I'm not quite sure why. So it ends up being that we can represent this part as between minus 1022 and plus 1024, and I'm not sort of seeing precisely right now why we sort of need to actually lose that last digit, but it has to do with this game of we've got 0 in the middle, so things are not quite symmetric. Other questions? Yeah, Stephen.
Does this mean that any conditional statement we write is at risk of?
It does indeed, and we're gonna talk about that in a couple minutes. Yeah. So you're basically asking if we use equals equals or similar sorts of things that we're, or for that matter, greater than or less than, that we're at risk of some of these. Yeah, exactly. Yep. So that's one of the main reasons that we're going through these sort of nitty-gritty details. Okay, so let's go back to thinking about integers for a moment. And we saw at the beginning of the unit last time, we said how big an integer can we represent, or yeah. And we said that the maximum integer we could represent in R, where was it here, is this value, 2 to the 31st minus 1. Okay. Oops. So let's go back and see if that's actually true. So I'm going to take x and make it 2 to the 45th. So that should be too large to represent, right? 2 to the 45th is obviously bigger than 2 to the 31st. And yet if I type in x, hey, things are fine. So if I type in z, okay, z is 25. And now if I ask what's the class of x and what's the class of z, it says they're numeric. Whereas if I say what's the class of, for example, 25L to force it to be an integer, then it says it's an integer. Okay, so we've seen this from a different perspective. We've seen that R basically, in most cases, makes integers into numeric values. This is the reason. We are able to store 2 to the 45th in a floating point representation with our 64 bits, but with our 64 bits, but with our 8 bytes. But with our 4 bytes that are used for an integer, we can only get as big as 2 to the 31st. So recognizing this limitation of integers, R is choosing to store numbers in general, most of the time by default, as floating points because it can store bigger numbers that way. So we can get around the issue. You know, so storing 2 to the 45th is fine if we do it as a floating point. And if I try and coerce it back into an integer, it's not going to work because I can't store a number that big as an integer. Whereas if I do that with 25, I can do that. Similarly, if I try and do something like this, I can't coerce 1 times 10 to the 308 back to an integer, but I can store it as a floating point, but I can't store 1 times 10 to the 309. Okay, questions or comments? Okay, so we can manipulate whether things are stored as integers. We've already seen this when we can use as.integer or as.numeric. We can also use the L notation, which stands for long, which is a long integer, although sort of forgetting off the top of my head why, at what point in history this was called L and a 4-byte integer was a long integer. In any case. Okay, so let's think about the precision with which we can store numbers and delve into that a little bit more. Okay, so we know that we have 52 bits to represent the D part of the number here. So I have D1 up through D52, but that's in base 52. Base 52. That's in base 2. Okay, so that means that we can store 2 to the 52 discrete different numbers. And 2 to the 52 is right around a half times 10 to the 16. So that's about how many discrete numbers we can store. So that's going to give us some idea of how many numbers we can represent accurately. And what that means is that real numbers on a computer are not continuous, they're actually discrete, because we can only store a discrete number of them. So math on a computer is different than math in real life, and a lot of the sort of things that we've learned about the basic properties of math in math in real life do not hold on a computer. We're only doing things approximately. So given that we can only store a discrete set of numbers, there are going to be cases where we try and store a number and it's not one of those numbers, and so it's going to fall into one of the gaps. And what's going to happen is the computer is going to represent that number basically by one of the two surrounding numbers. And so there's going to be some loss of accuracy in representing that number. And that's basically what we were seeing when we were looking at all those numbers, 0.1, 0.3, 0.2, that were not represented exactly. Okay, so we've also seen that we can change the exponent. So basically we can change the magnitude, and the absolute accuracy of our numbers is going to change depending on what the absolute magnitude of the number is. But the relative accuracy of our numbers is basically going to be the same, sort of normalized to the magnitude. And the result of this is we're going to have basically 16 digits of accuracy regardless of whether we're working with a very large number or whether we're working with a very small number. So basically the spacing is determined by the fact that I can, if I'm thinking about the spacing between numbers, suppose I have some number represented in this fashion. And the smallest amount I can increment this number by, let's assume for the moment that it's a number around magnitude of 1, and so we'll just keep this fixed. I can increment that number by just adding 1 in this position to that number. And that's going to tell me the spacing between this number and the next number that I can represent in this discrete representation. Okay, so that is called the unit in the last position, or the least significant digit. And we can basically explore what happens in terms of accuracy of different magnitudes of numbers based on that idea. So let's go ahead, and I'm going to look at this number. So I'm going to do a lot of games with numbers where I represent them as either 1, 2, 3, 4, 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6, 7, 8, so that we can sort of easily see what position we're in. That's the reason I'm using these particular numbers. So if I do this, I can see, okay, this is a number sort of like what we were saying, like 0.1, 0.3, 0.2, 0.3, those that magnitude of numbers. And indeed, we see the same thing here. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 if we round the next position here. So 16 digits of accuracy. And in this case, it's the 16th decimal place because it's a number of a magnitude around 1. Well, okay, let's start thinking about numbers that are larger or smaller. So from what I've just said, we should expect we're not going to have 16 decimal places of accuracy in this new larger number because the accuracy we have is relative to the size of the number. So if I look at this guy, and I look on out here, this one gets a little confusing because it shows quick 1s, 2s, and 3s, and 4s here, even though they're not actually accurate. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 4. So we're accurate up to here. Actually, we're accurate up to 17, probably just by happenstance that we were able to get a number that was the next nearest number probably just happened to have a 1 here, and so it looks like it's accurate to that position. But sort of leaving that detail aside, here are 16 digits of accuracy, but only 12 decimal places of accuracy, because we've used up 4 of our digits of accuracy out here. And we can continue this game here. Now I've got only 4 places of accuracy after the decimal place. So again, 16 digits of accuracy, but I'm not getting accuracy into the decimal places that I had before. And if I do it here, not sure if, yeah, I guess it's probably that it's actually representing this number as this actual integer value. So again, we're seeing, okay, we've got 16 digits of accuracy and not accuracy after that point. And now we start to get into the question of how big an integer can we represent exactly. If I try and do this, again, I've got 16 digits. This was a 20-digit number, and you can see things go haywire in these 4 positions here. So I'm no longer representing an integer this big precisely because of the fact that I've basically gotten beyond the number of digits that I can represent precisely. Okay, questions at this point? Yeah, Jimmy.
Will the imprecision part change? I mean, like, in my computer, it generates like the same imprecision part.
Sorry, I didn't quite hear that.
The imprecise part, like basically the same in every computer, or like.
That's a good question. I don't have a great sense of how much things vary depending on the hardware or the operating system that you're using. I mean, it would be interesting. We could go to Python, for example, and see what happens here. I do think this is, I mean, the Macs are built on Unix anyway, so that's not a particularly good test. But these, I think I'm getting the exact same things as on my, as my Linux machine. But let's, oh, okay. Well, Python's a little bit different because Python can store basically integers in arbitrary precision, so this is not a great test. 1, 2, 3, 4, 1, 2, oh, I guess this was 4, 8. Okay, so 1, 2, 3, 4. Okay, so let me try and force this into a floating point. The problem is I'm not sure how to get more digits in Python. Does anybody know? So I can't quite test this here to see what does it think is after the 4 here, or is it just representing this as exactly that? So I'm not quite able to ferret things out here. So I guess that's not a very satisfying answer to your question. Okay, so other questions? Okay, so let's start to think about what are the implications for this for doing calculations, which is going to be one of the main things that we're concerned about here. Okay, so here I've got a number, I've got 2 numbers that I should be able to represent precisely. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and then there's a 7 here instead of an 8. So the difference between these 2 numbers is just 1. I can hopefully do that accurately. I do indeed get back 1. But now I'm gonna put in 2 numbers that I can't represent accurately. I know the answer to this question arithmetically is just 1 as well, but I get back a 0. Okay, and the reason is we've already seen that I can't represent either of these two. I can't represent either of these 2 numbers accurately, and therefore it's not surprising that I can't get the difference between them accurately. I could also ask the question of, what if I am looking at it this way? This is the difference between these 2 numbers is going to be 10,000, and the difference here is in the 16th position. So I might hope that I could be able to do this subtraction accurately, because I can represent the result of this certainly accurately if I just do the answer and then put the answer into the computer. Okay, but we see that this wasn't done accurately either. And the reason is because I can't accurately represent the first, those 2 numbers that I'm putting in, so I can't get the result accurately. I guess it sort of depends on whether you're thinking about these things in absolute terms or relative terms. In absolute terms, I'm quite far off. The real answer is 10,000, and I'm 240 off of that. In relative terms, the size of the error here, the 240 error, relative to the size of these numbers is minuscule. So it depends on whether we're thinking about things in an absolute sense or in a relative sense. And I can play these games with small numbers as well. So here's 2 numbers I should be able to represent accurately up to that 16th position, which is the last digit there, the 8 and the 7. If I do that, I get back 9 times 10 to the minus 17. If I round that, that is 1 times 10 to the minus 16. So I am essentially getting an accurate representation in terms of in terms of the limits of which one was that? Sorry, in terms of the limits of what I'm able to do here. This, however, is an example of what we're going to talk about on Friday that's called catastrophic cancellation, which is that I know the answer to this question is precisely 1 times 10 to the minus 16. I can represent the number 1 times 10 to the minus 16 if I just enter it into the computer accurately up to 32 decimal places. So 16 digits of precision plus the 10 to the minus 16 where I'm putting that into the exponent part. Right, so this is represented with quite high accuracy out to the 32nd decimal place, 16 digits of precision. This is much less accurate. Right? This is only accurate essentially to one position here. And none of these digits are accurate and are not comparable to either the zeros or the nines, that I would be using to represent this number accurately. And basically the reason is what's called catastrophic cancellation, that when I do this subtraction, all of these numbers which were represented accurately are the things that cancel out with each other, and I'm basically losing those digits of accuracy. I've sort of thrown them away in the process of doing the subtraction. And the only digit that I have left that was accurately represented when I started the subtraction is this one. So that one is represented accurately. But since none of these remaining digits here or here were represented accurately, what I'm getting back here is not an accurate representation of the result. Okay. So there are lots of cases, and we'll see this in more detail, where if we do calculations, we can see that we lose digits of accuracy when we do certain kinds of arithmetic calculations with numbers that are either very similar in magnitude or very different in magnitude. Questions or comments? Okay, I can continue to play games here. Here I get back a 0, even though the answer should be 1 times 10 to the minus 20, it looks like. Okay, so I've basically lost all of my digits of accuracy here. Well, I mean, maybe in some sense I haven't. I mean, the answer is 1 times 10 to the minus 20, so 0 is sort of accurate up to a certain place there. And I could think about doing this with small numbers as well. So these numbers can be represented accurately up to the 20th position because I have 16 digits of accuracy. These zeros are represented as part of the exponent. And when I do that when I do that calculation, similar answer. I had this come in if they're sort of not as close as we'd expect, which is, I'm not quite sure why I had that in there, because 8 times 10 to the minus 21, if I think about rounding that, that is 1 times 10 to the minus 20. So we do have essentially accuracy in that single position that that single first position there. Okay. And then, so we've already seen a case of subtracting two numbers that were very similar in magnitude, and we saw that this catastrophic cancellation occurs. I could also think about subtracting two numbers that are very different in magnitude, and we could think about what will happen here. So if I do this, I sort of did this calculation by hand, and the correct answer is this number there. So what do you think is going to happen when I subtract these two numbers in terms of what I can accurately represent? So do we think I'm going to be able to accurately do the subtraction of this minus the integer part of, or minus the part of the number bigger than 0 here? Should we just try it? All right, so in some ways the answer isn't really all that different than what we've seen in terms of representing numbers. This number can be represented accurately up to 0.0000. This number is represented accurately all the way out to here, but all of these numbers are, when we do the subtraction, are not going to be paired with accurate representations in terms of this number, whereas these would be. So basically, we're only going to be able to get out here in terms of accuracy. And that's exactly what we see. We're fine in the first 12, which are the numbers before the decimal place, and then we're fine in the first 4, but this part of the number is, we're not getting anything useful out of that. Okay, so there's another definition of machine epsilon, which is, it's basically telling us about the relative spacing of numbers. So one way to define machine epsilon, which I'm calling epsilon here, is let's see, so first let's think about numbers that are right around 1. So we can think about, here's 1, 1.000 up to the 52nd position times 2 to the 0. And here's the next incremented number where I just increment the 52nd bit to be a 1 times 2 to the 0. Difference between those two numbers in absolute terms is 2.2 times 10 to the minus 16. So that's what we saw to be machine epsilon. So that's the absolute spacing of these numbers when the magnitude of the numbers is around 1. If we just start incrementing in this position, we're going to jump by that amount at that point. But it's also the absolute, it's also the relative spacing for numbers that are a different order of magnitude. So if we think about the relative spacing for some number x, and x can be of any order of magnitude, then if we increment by epsilon, then so basically what happens when we increment a number where we now are using the base to represent larger or smaller numbers? Well, I increment the d part of the number by epsilon, I'm then multiplying by a magnitude of x that's represented by the exponent part. And I'm subtracting off x, the value itself, and then in relative terms I'm going to divide by x, and that's just going to give me back epsilon. So that is also going to represent the relative spacing. So if I had a number like 1 times 10 to the 6th, then the error or the spacing in representing a number of this magnitude is essentially, in absolute terms, is going to be x times epsilon. So in this case, that would be 2 times 10 to the minus 10. The error is actually about half of that rather than the full spacing, but that's not a big deal. But we would also see that the relative spacing is still 2 times 10 to the minus 16. So we can actually see this if we actually look at various numbers. So I forget why I had this in there. Not quite sure what I meant to say there, except obviously that's the number that I had in what I was saying before. But let's think about incrementing numbers that are much bigger than 1, and let's look at the spacing that we see with those kinds of numbers. And this is going to playing around a little bit more with this is going to, I think, is going to be one of the problems on problem set 4. So I can calculate 2 to the 52nd. That's that value. I can get 2 to the 52nd plus 1. That's just incrementing that value by 1. These are actually represented accurately. And I can do 2 to the 53rd, and that's actually accurate as well if you just work it out. But now if I try and do 2 to the 53rd plus 1, something interesting happened. I didn't actually change the result, so I'm still at 992 here. And if I do 2 to the 53rd plus 2, I'm at 994. Okay. So that's a jump of 2. And so basically what happened was, it looks like I can't get the 993 number here. I can't increment by 1. And that has to do with this issue of spacing. Basically, once I get to a number that is this big, the spacing between the numbers is now 2 instead of 1. Okay. And that's the absolute spacing between the numbers. So you're going to play around with that a little bit on the problem set, I think. This actually works in terms of what I was giving as that sort of rule of thumb before. The absolute spacing is x times epsilon times machine epsilon. So when we get a number that's of magnitude 2 to the 52nd, 2 to the 52nd times 2 to the minus 52nd, that's machine epsilon, is 1. So the spacing is 1 for those numbers. But once I get to 2 to the 53rd and multiply that x times epsilon 2 to the minus 52nd, the spacing is going to be 2. So this also tells us how big can we represent, how large an integer can we represent exactly in base 2 given our representation and given this kind of spacing that results from that representation. So any number that I represent up through 2 to the 53rd, which is any integer up to 2 to the 53rd, can be represented exactly. But once I get bigger than that, I start to lose the accuracy. And if you wanted to play around, you could also play around with this for numbers that are very, very small and see what happens with why it is precisely that, for example, if I have the number 0.1, you could figure out, if you play around with this mathematics help for representing numbers in higher precision, you could figure out that this is actually the nearest base 2 representation of 0.1 that we can come up with. Or I'm not sure if that's quite accurate. It's either the nearest one or it's one of the two numbers that brackets 0.1. So it's in that sense it's accurate. It's sort of nearly as good as we can do. So this is not, what you see here is not arbitrary. It comes from what numbers can we represent, what are the discrete numbers that we can represent, and then where does my number that I'm interested in fall, right, in terms of then choosing between one of the two numbers that brackets it, one of the two discrete numbers that we can actually represent in base 2 with our representation here. So if we play around with this a little bit more, must not have changed the R code file because I have I have a little bit of extra stuff here in the notes, so I'll just type this in. 2, 3, 4, 5, 6, 7, 8. Okay, so here's a number. We can only represent it up to 16 digits of accuracy. Not too surprising, we've now seen that a number of times. I can try and change that number by a little bit, and I get a different representation. Again, only accuracy up to 16 places. But if I now change this by 2, or by 3, or by 4, I can sort of see what's happening here. I have this representation, then when I change it by this much, this is the next discrete number that can be used to represent numbers around this magnitude. Then I increment it by a little bit more, and I don't actually change which one is chosen. And then I increment it by a little more, and I do change what's chosen. So again, this has to do with, I have this discrete set of numbers. I have these numbers that I'm trying to represent with those discrete numbers, and it's a matter of sort of which one gets chosen as I sort of move along and positioning myself within this discrete set of numbers. So let's quit there, and we'll come back, and on Friday we'll talk about what are the implications of all this for doing comparisons, going back to Stephen's question, and what are some more of the implications of this for doing calculations.
Do you know if there's a way to temporarily use a higher number of bytes per number? That way, when you do a calculation that's higher than 10 to the 16th, your calculation will be more precise.
Yeah, so you can. I'm going to talk about that a little bit. There's a package called RMPFR that I'm going to talk about next time. You could also go and use Mathematica to get higher precision, for example.
Like symbolically or something?
I don't know off the top of my head exactly what Mathematica is doing. I think there's more. I mean, it does something symbolically, but it also, I think, allows you to represent numbers with more bits, which would allow you to do the calculations with higher precision.
Do you know if there's a way to do that from the system itself instead of just the programming languages computations?
I mean, I think it's. I don't know I'm not sure. There probably is. I mean, basically you're saying that you want to represent things as sort of a long double or something like that.
Yeah. Okay.
Hey.
How can you bring the old homework, the last year?
The ones that I was returning to? Yeah, I think I have those in here. I think I've been carrying them around for a while. Yeah. Actually, some of these are problem set 1 as well, so it looks like there's problem set 2 straight.
There's
You
mine.
actually saw it.
Yeah.
Okay.
I'm gonna give you half of
Oh,
them.
they're. It's okay.
Oh,
They're
you found it?
alphabetical.
Oh, okay.
So